Some people love it, some people hate it, but it should not be a surprise to you guys that Olympiad geometry is intimidating. It is intimidating because it is seen as something really complex, really intricate, especially with the diagrams that look like a complete spider web. For example, this one, or this one. It doesn't make any sense to the naked eye, but what if I tell you that there's a way to train yourself to deal with this level of complexity in a more strategic, in a more systematic way? Well, in today's video, I'm actually collaborating with an IMO silver medalist in 2023 from Australia named Christopher Tran, and we'll be tackling a somewhat infamous problem from IMO 2011, which only got 6 solves out of around 600 contestants in contest. However, we'll be presenting 2 solutions that everyone watching this video can understand and even come up with if given the right heuristics. The heuristics we'll be presenting in this video are curiosity and linking information together. We are talking about IMO 2011 problem 6. So here's the problem statement. Given an acute triangle ABC, we draw its circumcircle, and we let L be a tangent line to this circumcircle. It can be any line tangent at any point. And we reflect this line over the 3 sides BC, CA, and AB to form a new triangle with another circumcircle. And the problem asks us to prove that the circumcircle of this new triangle is tangent to the circumcircle of ABC. So as you can see, I've drawn this diagram over here with the main triangle ABC and a line tangent to the circumcircle of ABC. I call the tangency point as P, as you see here. And then I reflected this yellow line over each side of the triangle and get a new triangle, the green one here. And they're asking us to prove that the circumcircles of ABC and DEF are tangents at some point. They're not telling us which point it is, which means that we have to characterize it on our own, right? So the first thing we see here is, hang on, I'll just draw these 3 intersections over here because like they seem like they would be useful points. I'll call this Z, I'll call this one Y, I will call this one as X. There you go. What we see is that AZ and AY are axes of reflection for the yellow line to get these 2 lines. Like, in order to get DE and DF, you need to reflect the yellow line over these 2 lines, and they intersect at A, which means that A actually has equal distance from A actually has equal distance to DE, DF, and ZY. Now this is where curiosity really comes in. If it is equidistant, what happens if we draw this circle over here? It's tangent to all 3, right? But can we go further? Can we utilize this idea and adapt it further? Well, we can actually, because it turns out that if this circle is tangent to D and DF, then if we draw the in circle of DEF and that is in center BI, then DIA will be collinear, but also in a similar fashion, BI and E will be collinear, CF and I will also be collinear. So we can start drawing this in center, and what we see is, wait, it actually lies on the circumcircle of ABC, right? And the way you prove this is that you angle shades for EDF, which is actually easier than you think, because in order to get DF from DE, you take DE and you reflect it over AZ, and then you reflect it over AY. And we know what the angle of ZAY is. It's actually just BAC. Therefore, what we get is that EDF is equal to 180 minus BAC. I'll show you right here. Right? We have 57.5 here, and we have 61.3 here. Right? When this is 85, this is 10. And I think you can understand what the proof of this is. I'm just showing you in order to convince you that this is correct. It doesn't even matter where P is, because at the end of the day, we are reflecting a line over two reflection axes, and the angle between ED and DF depends on the angle between BA and AC alone. So let's get back on topic. Since we know about every angle in DEF and even the orientation of each line, how is it that it is still so disconnected from ABC? Well, we need something in the middle to link them together. We are going to create a smaller copy of DEF that fits right into ABC. How do we do this? Well, we actually use the power of hindsight to construct these 3 points first, in hopes that we can, in the future, characterize these 3 points without utilizing S. Because at the end of the day, we are trying to prove that S exists, right? Here's how we do it. So, one heuristic that I usually use in contests or when I do geometry is that I keep a mental mark of which lines or which points can be angle chased. And what we know here is that EF, DF, and DE can be angle shades, and so there has to be a simple way to characterize E1, F1, and D1. But how do we do that? Well, if you observe it, you see that EF is perpendicular to the reflection of OP over BC, right? Because like OP is perpendicular to YZ, right? So if we draw this point over here, where if we draw this point as P1, such that P1 and CB are parallel, then what we get is that P1 E1 is equal to P1 F1 because OP1 will be perpendicular to E1 F1. Wait, no, I drew the wrong line. Yeah, this one. Like, you see how these two lines are perpendicular? And what's even more fascinating is that since we wanted EF1, we wanted E1 D1 F1 to be equal to 180 minus 2 times BAC, right? This means that we want E1 P1 F1 to be the same angle, right? And what we essentially do here is that we chase for E1 B P1, and we will see that this actually forces E1 F1 P1 to be equal to BAC, because like it is an isosceles triangle after all, and the vertex of this isosceles triangle has an angle of 180 minus 2 times something. So that something has to be the base of the triangle, right? I'll show it to you here. BAC is 61.3, this is also 61.3, this is also 61.3, right? So what you have here is that E1BP, E1BP1, sorry, it's actually equal to BP1C, actually equal to P1CF1. Therefore, E1B and P1C, they have the same length, like the exact same length. But this also means that E1B1 and BP also have the same length. And now we can define E1 F1 D1 differently. We can first define it as the unique triangle that is a dilation of EFD that has the same circumcircle as ABC, and we can show that BE1 is equal to BP, and this allows us to redefine E1, D1, and F1 again by discarding this, and instead define it as this point where BP and BE1 are equal, like this. and also like this. And keep in mind that this angle equality will help us somewhere in the future, because this is a huge resource, right? In fact, we can already see its effects here, right? Now, why is it concurrent? It is concurrent because E1CB is equal to F1BC, right? And these are actually equal to CBP and then BCP. This means that this concurrency point is actually the reflection of P over BC. I'll call it Q1. Q1 because, like, without hindsight, we do not know if we would need to construct the rest of the diagram because we are just isolating it to A here, right? Now, we have gotten ourselves this funny small triangle, which is almost identical to the big green triangle, except it's smaller. And what we need here is that we have to show that EE1 and FF1 intersects on the purple circle. They intersect on the circumcircle of ABC, right? And the last step of this actually requires quite a bit of creativity. It's not a difficult move, but it requires a level of curiosity nonetheless. The curiosity I mentioned comes with the step of trying to characterize S, because, like, surely it can't just be a random point that's just floating on the circle if it has this much significance. And as it turns out, there's a cyclic quadrilateral here. There's also another cyclic quadrilateral here, right? Once again, I will use the color cyan here. And this is surprisingly easy to prove, because firstly we have to prove that these two cyan circles and the purple circle intersect at one point, right? And the way we do this is that we chase for B as Q1 and C F Q1. The way we do this exactly is that we want to show B as Q1 plus C as Q1 equal to BAC, and this is equivalent to showing that B1E Q1 plus CFQ1 is equal to BAC, but we just did that when we constructed the Incenter here, because, like, BEQ1 plus CFQ1 is just IEF plus IFE, right? Which has to be equal to BAC. Therefore, we've established that EBQ1 and FCQ1 have circumcircles that intersect on the circumcircle of ABC. And the last step here is proving that E1SB is equal to ESB. And the way we do this is that we ask what else is equal to ESB. Of course, it's EQ1B, right? You see where it's coming to, where the resource is coming now. All the way back then, when we proved that Q1 lies on all of these three lines through, like, reflecting P over BC, it's getting used now because EQ1B is actually just BPC. BPC, what is BPC? It's BAP, right? BAP, I'll just show it here. BPC is equal to BAP, also equal to BE1P equal to E1PB equal to E1SB, right? We went all the way from ESB, traveled this far, and got to E1SB in the end. And this proves that E1 and S are collinear, right? And also F1 and S are collinear. But since E1DF1 and EDF are dilations, S must also lie on DD1. And since we've established that S lies on the circumcircle of ABC, we're actually done here, because if we start a dilation from S sending E1, D1, F1 to EDF, it's just going to enlarge the circle that is already on. and this means that it will be tangent to the original circle no matter what. So this is the entire solution, but there is a cleaner solution with another heuristic that my friend over here, Christopher Tran, will be presenting right now.
So we're given a triangle, ABC, and we're given a tangent to its circumcircle. And we're asked to reflect that tangent in the sides BC, CA, and AB to get these three red lines. And we're asked to prove that the circumcircle of the triangle determined by the three red lines is tangent to the circumcircle of ABC. Now, tangent circles, a big theme in Olympiad geometry. There's a lot of ways to prove that circles are tangent, but one of the really common ways, especially at a high level, is to figure out what this tangency point is and characterize it as a Michael point or an Anti-Steiner point. What is an Anti-Steiner point? Well, the Steiner line is an analog to the Simpson line. The Simpson line allows you to take feet, the perpendiculars, from a point on the circumcircle to the three sides, and then those 3 feet will be collinear, and that line will bisect the line joining the point to the orthocenter. The Simpson line is basically a dilation of this by a factor of 2 at the original point D. Instead, we reflect the point in each of the sides, D to U in BC, D to V in AC, and D to W in AB. And these will be collinear with H now, because instead of passing through the midpoint of DH, it passes through H. This is quite nice. And so we're going to try, and so if we do this in reverse, so take a line through H. What point is this the Steiner line of? So if we take DH, if this is the Steiner line of some point on the circumcircle, then, well, it contains the 3 reflections of the point in the sides. So if you reflect this line in the 3 sides, they should concur at the point. And so if we reflect, well, they concur at a point, and it's already spoiled for you, it is the tangency point in the problem. So this is our theme. We're going to try and prove that the tangency point is the Anti-Steiner point of D. Well, line DH or D, because you just joined D to H. And for now, we're going to ignore the fact that this line is actually tangent, and you'll see why. But the motivation for that is that the Anti-Steiner relationship doesn't really lend itself too well to actually using the fact that the line is tangent. So I said that the other theme was that it would be a Michael point, because it's really hard to, deal with an Anti-Steiner point except through some reflection like cyclics. So what if it was a Michael point? Well, we're trying to prove that it lies on a circle determined by 3 lines. And a common Michael point theme is to find the 4th line. And looking at our diagram for a little bit, it's right here. The Michael point, if those 3 red lines and our Steiner line, is in fact the point we want. And this helps us do those cyclics, because if we can prove that the Anti-Steiner point lies on these 2 cyclics, then we will have proven it lies on this cyclic by Michael. So let's try an angle chase. EVX, where can this go? Well, we can actually reflect in the line AC, because both of these lines are formed from reflections. Indeed, V is the reflection of D in AC, and DH passes through the reflection of E in AC. So the reflection of line EV in line AC is in fact line DH, while the reflection of VX, well, VX was the reflection of the tangent in AC. So angle EVX in directed angles is equal to the angle between the tangent line and DH. Well, yeah, because the GeoGebra is drawn in the wrong direction. However, via the exact same reflection trick, this angle will equal EWX, because the reflection of EW in AB this time is DH, and the reflection of WX in AB, well, that's the tangent line again. So we've shown that EWVX is cyclic. By a similar angle chase, we find that EWYU is cyclic, and therefore E lies on the circumcircle of XYZ. But wait, how do we prove that they're tangent? We use a neat little trick. We never use the fact that this line was tangent to the circumcircle. So if we did it with a different line, something like this, and we drew the 3 reflections, this will get a bit messy, but we'll handle it. And we intersect the 3 lines. Oops. Is that the correct intersection? No, it's not. Okay. It's that line, that line. It's those 3 lines. Okay. Nope. Nope. Okay, I'm gonna have to zoom in. And draw the circumcircle. Wow, it passes through E. And we didn't even use the fact that it was tangent. But let's flip this argument. By looking at F instead, the circle also has to pass through the Anti-Steiner point of F, right? And indeed it does. Right? So, what happens if we move F on top of D? Well, look, K is going to move towards E. And in fact, when F equals D, K equals E. So, the circle in the problem, if you generalize it to a random line which intersects the circumcircle twice instead of a tangent, it will intersect circumcircle ABC at 2 well-defined points, functions of the 2 points. And so, when we put them on top of each other, the 2 intersections are the same. And this tells us the circle is a tangent with no extra work. And that concludes the solution.
Both of these solutions demonstrate curiosity and the idea of linking things together in their own ways. Starting with my solution, the curiosity part comes when I asked about A being equidistant to both the original line L and also LB and LC, right? And when I saw that, I was like, wait, what if it's the excircle of something? What if I draw the perpendiculars and create a circle? Oh wait, it is the excircle of something, it's the excircle of DYZ, right? What if I draw the incenter of DEF then, right? This is the curiosity part, and the part where I link things together is that I knew everything about the angles of each line in LA, LB, and LC, yet I know nothing about the positions of D and E and F, right? So the part where I link things together is that I create a copycat of DEF within ABC, a smaller copycat, right? Because I knew that this has to be used as an intermediate in some way. And for Chris's solution, the part of curiosity is that even if you never knew about the Anti-Steiner point, or you never even heard of the Simpson line, you can think about this. If we reflect the whole line, what happens to the initial tangency point? It seems important, right? So we can also reflect it over with them and see what happens. This is a really natural way to discover the Simpson and the Steiner lines, as I did discover this myself at one point as well with another problem. And the part where he linked things together is that he anticipated that there are more circles going through that tangency point. It has to be an equal point of some kind, because D and E and F, they are a little bit too random to be on their own. So yeah, that does it for this episode. I hope you guys enjoyed this. Thank you for watching. See you next time.